So I will go to the Notepad++ once again. I will create a new file. So Control N. Now again, first I will save this file. So click on File, Save As. Now because this is a test bench, so I will save this in this test bench folder. Okay. And give it some name. This is Shift Register underscore TB. Okay. Now click on Save. So first I have to give the library declaration, then entity declaration, and then architecture declaration. Okay. So what I will do that I will copy the whole code from here and then just paste it. Okay. Okay. So you can see the details are not same and the keywords are not highlighted here. Just because that I forgot to save this file as .vsd or as an VHDL file. So let's save this once again as .vsd. So this is shift register underscore TB and this is basic hardware description language. That is VHDL file. Okay. Now click on save. Okay. So you can see that we have library declaration and we have this entity declaration. Now because this is a test pen, so we actually do not need this. So let's delete this part. I will keep this generic part here in this entity section, okay? Because I'm going to use this in the later part of this code, okay? And now I will delete all the architecture part from here because we are writing the test bench here in this code. And for this, I will need this entity section of this shift register module. So what I will do that I will use this part of code to define the component. Okay. So now this is a component. So this is component shift register is and in the last and component. Okay. And now I have to define all the input output ports as a signal, right? So this is just a standard structure, right? So let's define all these ports as signal. So this is signal clock. Next, this is signal reset. Next, this is signal shift enable. We have signal D in and we have signal D out. Okay. And in the last semicolon. One more thing that we cannot have the same module name in the same project. So let's change to this shift register underscore TB because this is test bench. So this is shift register underscore TV. Okay, so that's look good. Now I will copy this component part from here once again, and I will paste this inside this architecture section after this begin keyword. Okay. So what I'm going to do here that I want to use that shift register component as a block here, right? And I will give the port map and generic map here in this section. Okay. So for this, first I will give the name to this component. Suppose this is UUT or unit under test. Now I do not need this is keyword after this. Now generic map and this port map. Now suppose data width is connected to data width. Okay. And MSB or LSB is connected to MSB or LSB. Okay. And we do not need semicolon here because this whole line of code is treated as a single statement. Although there are multiple lines, but these all line of codes are treated as a single statement. Okay, so there is no semicolon here. Now port map, so clock is connected to clock, reset is connected to reset. Okay, so reset, shift enable is connected to shift enable. Now this T in is connected to T in and this T out is connected to T out. Okay. And we do not need this AND component part here. Okay. So that is our component mapping. Now first we will define this data width and MSB or LSB generics. Okay. So our data width is suppose 8 and our character and I want to send LSB first. So this is L. Okay. Now we will write the VHDL code to drive all of our input ports, right? So we have these input ports in this shift register module. So let's define the clock first. So I'm giving the initial value to this clock signal. Okay. So let's create a clock signal of 50 megahertz first. So this is clock is equals to, or clock gets the value of not of clock after 10 nanosecond. Okay. So that is our clock signal. Now we will write the process to drive all other input signals like reset, shift enable and D in. Okay. Okay, so let's write the process to drive all the input signals or all the input ports, right? So let's give it some name first. So this is TB underscore process. Now this is process. Now I will not write anything in the sensitivity list because we are going to use wait statement for this process. Okay, so TB process colon process, then begin, and in the last and process. And before this, I will use wait statement. Okay, because this whole process will be only executed once. And once this wait statement is triggered, then our simulation will stop here. Okay. Okay, so let's write the code for this process block. So at the initial state means at 0 timestamp, we have reset, that is asserted. So this is 1. Now suppose we have this shift enable. So that is 0. And we have this D in, and suppose this is logical high. Okay, because that is our ideal state. Now I want to wait for 100 nanosecond. Means this reset will be asserted for 100 nanosecond of time period. Okay. So after this 100 nanosecond, first this reset will be 0. And then I will wait for another 100 nanosecond. So wait for 100 nanosecond. So wait for 100 nanosecond. So that's good. Now this is the time when I need to capture D in one by one based on this shift enable signal, right? And we need to capture this D in 8 times, right? Because we are using the data width of 8 bit, okay? And I also wanted to send this D in at the mid of some baud period, right? So what I will do that I will wait for another 4.35 microsecond. Now this comes because we are going to use the baud rate of 115200 and that will have the period of 8.7 microsecond. So this is about the halfway of 8.7 microsecond. Okay. And now suppose the data is hex 51, which we are expecting to receive at this UART receiver, right? So suppose this value is hex 51 means the binary value will be 01010001. Okay. Now because we are using the RS-232 protocol, so that is sending the LSB first, right? So this 1 will transfer first, then this 0 will transfer, then this 0 will transfer, then this 0 will transfer, then 1, then 0, then 1, and then 0, right? So let's write this. So wait for 4.3 microsecond. Now this D in will get the value of LSB. So that is 1 here, right? But here we have one problem because this D in can be received at any point of time and that is not synchronized with your FPGA boot frequency. And if you remember from our shift register module, then this shift enable input is synchronized with your rising edge of clock signal, right? So there is no guarantee that after this waiting period, we also have the rising edge of clock, right? So to drive the shift enable, we actually have to wait for the rising edge of clock signal. Okay. So we will wait until rising edge of clock, right? So what will happen? That shift enable will get the value of 1 means we will asserting the shift enable signal and this shift enable pin will be logical high for complete 1 clock cycle. Means at the rising edge of next clock cycle, so wait until next rising edge, so wait until rising edge of clock, this shift enable will be logical low. Okay, so for this clock cycle this will be logical high, and after this clock cycle for the next rising edge this will be 0. and then I will wait for another 4.35 microseconds. So wait for 4.35 microsecond. Okay. Now these multiple line of code is just transferring this one bit of data. So I have to repeat this whole code 8 times, right? Like this. So instead doing this, what I will do that I will create one another signal. Suppose this is packet data. So define the signal. So we have signal packet data, and that is std logic vector data width -1 down to 0. Okay. Now because these are signals, I do not need to write the port direction, right? So let's remove this from here. Otherwise this will give the syntax error here. Okay, now this looks good. So what I will do that I will assign some data to this packet data. So suppose our packet data is 51. Okay, so this is the packet data. Okay, so that is 01010001, means that is hex 51, right? Let's move this. So what I will do that I will use a for loop. So let's see how we will write this. So for I in 02 packet, or sorry, data width -1 loop. So this is for I in 0 to 7 loop because data width is 8. Okay, let's move this further and add a loop. Okay, and now because we are capturing the D in input here, and that is depends on this packet data. So I will modify this hard coded one to this packet data. Okay, so packet data index I. Now because this is 7 down to 0, so this is 7. So this is 7 and this is 0. So when the value of I is 0, we will capture this 1. When the value of I is 1, then we will capture this 0 and so on. And that will repeat up to 8 times. Okay, so that looks good. Let's give a quick look to the code. First, we have this library declaration. Then we have entity declaration, and we also have generic defined here. And we have also initialized the generic values. So data width is 8 and MSB or LSB is L. Means we are sending the LSB first, right? Entity name is correct. So that is updated. Architecture behave of shift register TV is. Now we have the component declaration. So that is good. Now we have defined all the signals. So these signals are coming from these input output ports of our shift register module. And we have also defined one another signal, that is packet data. And the packet data value is hex 51. So it's this value in binary. So here we are driving the clock signal, and that will be generating 50 megahertz of clock signal. Now this process is for driving the input output ports of this shift register module. So we have this reset 1, shift enable 0, D in at the very starting of simulation. Then we will wait for 100 nanosecond, then reset will be 0. And that will be applied for 100 nanosecond. Then after this, we will drive this D in. And for that, we have used this for loop statement. And here we have this component mapping. So we have generic map and we have this port map. So let's save this. And now we will compile it and see if it is having any syntax error or not. So for that, we will go to this model sim simulator, right click, click on add to project and select this existing file option. Now click on browse. Now select our project folder and go to this test bench folder. So we have this shift register underscore TB. So select this and open. Click on OK. Now we will compile it. So select this file, right click and then compile selected. Okay, so we have this one error. Let's see what it is. So that's saying okay, so there is some spelling mistake somewhere, packet date. Okay, so let's correct it. So this is packet data, Control S for save. Now close this and again we will compile. So compile selected. Okay, so compile of shift register underscore TB is successful. Okay. Now we will go to this library tab and we will look for the work library. Okay, so we have this work library here. Now select the shift register underscore TB and click on simulate. Okay, so the simulation window is opening. So I am interested in this UUT. Okay, so I will select required ports and signals. So I'll need this clock signal. I need this D in, I need this D out, reset, shift enable, and this shift register register. Okay, so drag them into the waveform. Now run this simulation for something around 200 microsecond. So run it for 200 microsecond. Okay, so let's zoom out. Okay, so we have all the pulses generated. So let's see. Okay, so let's change the radix to the hex so that we can easily visualize it. So this is hex and this is hexadecimal again. Okay, so till this 100 nanosecond, we have reset, that is high. Okay, D in is logical high and shift enable is 0. That we have defined in the test bench, right? And after this 100 nanosecond, this reset is deasserted. Okay, so now zoom out little so that we can see the pulses. So you can see that we have generated 8 pulses here. So this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now if you focus on this shift enable, so we have generated this first pulse here. And at this moment, we have captured this D in input. So that is 1. Next value is 0 for the next pulse, then 0, 0. Next 1, 0, 1, 0, right? And that was our data. Okay. So remember, we have provided the data hex 51 means the value is 0, 1, 0, 1, 0, 0, 0, 1. Okay. Now, because we are transferring the LSB first, so first we have captured this 1 here. Next, we captured 0. Then we captured 0. Then 0. Then we captured 1. Then 0. Then 1. And then 0. Now, if we expand this D out, so that is our index 0. Now, when this first pulse on this shift enable is asserted or captured, then this D in data, that is 1, that is captured by this 7th index, right? And at this second pulse of this shift enable, this D in value, that is 0, now it is captured at the 7th index, okay? And this 1 is shifted to the next index of this shift register, right? And that is happening 8 times. And in the last, when all the data of this D in is captured one by one, we get our data, right? So that is 51. So that's how this shift register works. We provide this D in input one by one, and at the output, we will get 8-bit parallel data, right? So I am happy with the simulation results now because we can see that is something we are expecting from our code, right?